this is the material for chapter 8 that covers, week 8 that covers chapter 29. So just some notation here. Whenever we have a vector coming out of the page, we denote it by a little dot like this. Going into the page, it's a little x. Whenever we have a current coming out of the page, all we do is add this little loop to kind of say that, well, it looks like a wire. And then here, whenever the current is going into the page, same deal with the loop around it. Now what we see is that moving charges create magnetic fields. Where that magnetic field is like pointing can be determined by the second right-hand rule. What you're going to do is point your thumb in the direction of the current. So here, in this example, the current is going into the page. So you're going to point your thumb away from you, and then you're going to kind of look at how your knuckles curl around your hand. And you're going to see that they curl this way, right? So like your fingers are curling clockwise. So we see that the current is denoted, the magnetic field is denoted as going clockwise as well. So that's how you kind of like intuitively figure out what it looks like. But now more mathematically, if ever we wanted to calculate like, okay, maybe we have a really weird wire that's a loop, and we want to know what is the magnetic field at this point P, we're going to use Biot-Savart's law here. What you're going to do is take a little chunk of your wire, ds, and you're going to say, well, ds, this chunk of wire that's going in the direction of I, is a distance r away from my point here. So we say that dB, the magnetic field due to that little chunk of wire here, is equal to mu naught, the permeability constant, it's just a number, divided by 4 pi, times I, the current, times ds cross r hat, where ds is again this vector here. R hat is a unit vector of r, which is going again from ds to point P, divided by r squared. We then would like to know, well, what are the contributions of all the little points along this wire? So we sum them up like this. This is kind of clearly a decently difficult equation to deal with. So normally we kind of have like tricks to get around actually having to calculate this. One of the tricks is known as Ampere's law. If you remember from many weeks ago, whenever we talked about Gauss's law, that was essentially a shortcut to finding E. So if you remember, we had a Gaussian surface. It was like maybe a sphere or something, and we wanted to know what was the electric field at some point here, a distance r away from that sphere. What we did was use this equation here, and what we saw was that when E is parallel to dA, E dot dA becomes EdA, and whenever E is a constant, we can pull it out, so we get E, surface integral of dA, which was just the surface area. We do a very similar thing here, where instead of having this surface, like this closed surface, we have a closed loop called an Amperian loop. What we then see is that this closed path integral of b dot ds, so it's ds, which is a little like a step along that path, is equal to mu naught times I in, where I in is the steady current passing through the surface bounded by the path. It's like, what is the current going through here? So then what we see is that if B is parallel to ds, and if B is constant, so we have here a little step ds, and then B is going along this direction here, we get B times then this integral, closed path integral of ds. All this is saying, it's saying take the circumference of the circular path. So like, what is the circumference? 2 times pi times r. So what we get is B is equal to mu naught I divided by 2 pi r. This is for the magnetic field due to a straight current carrying wire at distance r away. So this is the magnetic field due to a straight current carrying wire at a distance r away from the wire. So it's like, what is the magnetic field down here? What is the magnetic field here? The same thing that we had before, where instead of having this closed surface, we just have a closed loop. So very, very similar. The next thing we can talk about is called the solenoid. So a solenoid is a helical coil of wire with current passing through it. So here we have this wire that's been looped around like this, and there's current passing through it. Now, if we make these loops tight enough, so close enough together, they kind of essentially start to look like straight lines here. Now, if we have, for instance, I draw these little like dots and these little like X's, this is just to know that this is where the wire is coming out, and then this is where the wire is coming back in. So it's like coming out here and then going back in, and that's how it's spiraling like this. Right, so what we see is that each field created by a loop looks like this. We're at the edges here, so at the edges right there, it's kind of curved like this. But then in the center of the solenoid, we're going to have this straight line. So we're going to have this essentially uniform magnetic field going in here, and about no magnetic field outside of the solenoid. What we see is that B, the magnetic field inside the solenoid, is mu naught times N, which is the number of turns per meter, times I. We're going to now just go ahead and prove that by using an Amperian loop. So what we do is we take our solenoid here, it's just represented by these dots and these crosses to not confuse us too much, and we place an Amperian loop like this. So part of it is inside the solenoid, and part of it is outside the solenoid. The current is going to the right, which is the same direction as the magnetic field. Instead of doing this integral all at once, we're going to just divide it up into parts. So we're saying, well, what is the integral along this path? What about this path, and this path? And then we're going to add them up. Now we know that the integral here for the left one is going to be b dot ds, where b and ds are perpendicular to one another, because the path here, it's going in this direction, which is again perpendicular. So then the sine or the cosine of 90 is equal to 0. Then this is 0. Same thing goes for the right. Because they are perpendicular to one another, this integral is equal to 0. As for the top, there is no magnetic field here, right? We said there's no magnetic field here, which means that this is equal to 0. The only one that matters is the bottom one. So we're saying that the integral of b dot ds here is equal to mu naught I in. Here, b is parallel to ds, so they're going in the same direction. So that means we can say b ds. And we can also pull b out because we know the magnetic field is uniform. Because of that, we can write it like this, where we're taking the integral from 0 to L, which is just saying like how long is our Amperian loop. So we have this integral, and then it simplifies down to just being BL on the left-hand side, and then mu naught N times I. The reason why we multiply by N is because we do have to take into account how many loops we have, right? So it's like here, are there like 100 loops? Are there 50 loops? This is a very common thing we do. We just multiply by N like this. And then the answer we get is BL is equal to mu naught N times I. Isolate for B, and we see this, where we define N, little n, to be the loop density. So how many loops do we have per unit meter? And that's N divided by L is little n. So B is equal to mu naught N times I, like we said up here. So next, we can talk about Gauss's law in magnetism. The idea of Gauss's law is it kind of takes into account how many magnetic field lines would a certain charge create at a certain distance away from it. So for instance, here, if I'm way down here, we know that the field lines, they kind of spread out over time, right? So if we have this positive one, it's going to spread out, and maybe the electric field here is going to be weak. It's going to really depend on here, how much charge do we have in this Gaussian surface? What we have in magnetism, however, is this requirement that we never have a monopole. So there's always a north and a south. So that means anything that's going out of the north always goes back into the south. So we're never able to get things that are just exiting, right? So this is exiting, so we have this net flux going out. But here, everything that comes out goes back in, so we never get this net flux. The flux is always equal to 0. So that's it for Gauss's law, really. Like, there's nothing more to say about it for now, of course. So we're going to move on to magnetism in matter. We've already kind of seen this last week, where we defined mu to be the dipole moment, which is just a vector that points here from the South Pole to the North Pole, but it's also equal to I times A, where A is the area vector. So if we have the surface here that's bound by this current here, mu is in this direction. Now, we can essentially have, I guess, like think about this like the positive part of an atom, and the electron going around in its orbit is creating this dipole moment. This doesn't always happen. You can go read your book a little bit more to get some more details about like why some materials have magnetic moments. But essentially we're going to say that sometimes materials do have magnetic moments like this. We can divide materials into three broad categories. The first being a ferromagnetic material, where the magnetic moments align, which creates a strong magnetization that remains after the field is removed. So this is a permanent magnet. The idea here, like magnet, you can think of it like how good is it at acting like this stereotypical magnet that you're, I don't know, trying to stick to your fridge. Where here, these represent the different magnetic moments inside. So they represent all these different atoms that are aligned like this. So they're all aligned in the same way. Even when you remove the magnetic field, so remove B, they're still aligned like this. So these are really, really good at acting like magnets. So this is like copper, or you have like iron, things like that. Those are ferromagnetic. On the other hand, we have a category called paramagnetic, where these magnetic moments are weak, and they're in some, but they are in the same direction of the magnetic field. What we mean by that is here, normally when there is no magnetic field, so they're just kind of like floating around in space, the dipole moments are all like messed up. They're all in random kind of different directions. So it's not acting like a stereotypical magnet. If you then place it inside a magnetic field, it's going to kind of align with the magnetic field like this. So you can see there's a bit of a wobble to it, but in general, they are pointing in this direction. But it is a weak magnetic moment. The last category we have are diamagnetic materials, where these magnetic moments are, again, weak, but here they're in the opposite direction of the magnetic field. What's also interesting is here, when there is no magnetic field, they have no magnetic moment. When we place them inside of a magnetic field, again, it's kind of weak, a little bit like wobbly, and in the opposite direction of B. So again, your textbook does go into more detail, and I'm not really going to talk about it in this video. But yeah, that's all I